Hello, everyone. So this is a presentation about a paper we will bring out. The title is Vacuum Energy, Casimir Effect, and Newton's Non-Constant. My name is Benjamin Koch, and the work has been done in collaboration with René Sedmick, Mario Pitschmann, and Christian Käding. And we hope to bring the paper to the archive. So the content of the talk is listed here. So we come from a short motivation to what we want to do, discuss different vacuum energy densities in the lab, in the universe, and so on. Then return to something which is needed in this context, the scale-dependent framework, and we will see how this can be directed towards experiment and observation. And finally, some discussion and conclusion. So for motivation, let me invoke a series of comics which circulated a lot in Chile, but maybe around the whole world, I don't know. About it's from Captain America. So let's get started. The point here is that there's a really big problem when we try to understand the vacuum, the nothing, in terms of quantum fluctuations in the context of cosmology. Of course, this is known as the cosmological constant problem, and it even heats up Captain America, who's a very kind guy, actually. So what do we know so far about vacuum energies? And there are two things we basically know. There's the quantum vacuum in the form of the Casimir energy. So here we see a schematic form of this experiment. So there are certain quantum modes allowed between two electric materials. And since you have this selection of quantum fluctuations differently from the inside and the outside of the experiment, you can calculate a net energy, which then would be a net force, or translated, if you want so, net energy density. So the effect of this, you have an acceleration of the plates. So the other thing which is known is the cosmological vacuum. We will call it here rho lambda. And this is, here's a picture of the evolution of the scale factor of the universe. This is observed in the late universe, that the universe doesn't not only expand, it expands accelerated. And here the people who got awarded by the Nobel Prize for this observation. So here the vacuum accelerates the universe. So, and we know these two things, and what we would like to know in our approach is how are the two things actually related, or are they at all related? So we have rho quantum on the one hand side and rho lambda on the other side. And this is, of course, seeking the connection. And if we find the connection, this would make us really, really happy. So let's get started and use an analogy, which is the construction site at our house, like a few months ago. And this analogy goes like this. So we faced a similar problem here. So we tried to find how things are connected here, are the tubes of the electric installation. And once you have too many tubes, you don't know which one is connected to which one. So how could you figure out what is connected? So yeah, the approach is you pull or you blow into a tube, and then you try to observe which tube has a reaction somewhere else, or moves or emits a noise. Yeah? So we try to copy this strategy here. And so now, first, we have a look at the Casimir effect. So in the laboratory, and this was predicted by Casimir in 1948, and then finally observed 50 years later in 1997. And one can associate to this energy density, even though things are in reality much more complicated. So this is just a oversimplification of ideal plates and homogeneous energy density and so on. But okay, this will serve our purpose for now. And if you have this energy density, you can relate it to a force, and a force to an acceleration. Okay, so in reality, there are additional effects, many additional effects. So let me mention a few of them. For example, in the experiment, there's finite temperature. So this modifies the dielectric and magnetic properties of the material. So there's a gravitational attraction between the plates, because the plates are massive, and well, there's more forces acting. And if the experiment is precise enough, it can actually measure this, observe this. And here we see the standard typical formula of Newton's law integrated over the two volumes and the mass densities, rho m, of the two plates. And here are the integrals. So they go over one plate and the other. And of course, Newton's second law is intact. And finally, there's a finite penetration depth. So the surface is not a perfect conductor, but the electromagnetic modes propagate into the surface. And this is known as a skin effect. And if the modes propagate into the surface, it's reasonable to assume that also the vacuum energy density is non-zero when you go into the material, and then it drops off, of course, just like the modes. The penetration depth associated to this we call lambda, and it's also a simplification, not a first principle calculation. Okay, but this is something one would reasonably expect. And okay, so we have now these modifications, and we would actually like to remember two of them, namely the gravitational force due to the gravitational potential and the finite penetration depth, because they will play a role now in what we discuss next. So before we go to this implementation, the other vacuum energy density, which is known in the universe. So, okay, what better than starting with Albert Einstein and his famous field equations, which you see here, and in red highlighted is the famous cosmological term. And if you look at these equations for a very homogeneous symmetric universe, the only degree of freedom remains the scale factor of the universe. And this is then also affected by this lambda term. And how is it affected? Well, you see the sec derivative is getting a positive contribution here, if lambda is positive. And this turned out to be actually in agreement with observation here. Again, Permuter, and Schmidt, and they made observations of different distance measurements, and could confirm that lambda dot is not zero, of course, and lambda double dot is actually positive, accelerated expansion. So the conclusion and simplest implementation is a positive lambda. So far, so good. So can one then interpret this lambda as an energy density? And this has a long history. So energy density, so that you get the units right, has to be something like lambda naught over G naught, as written here, and would be 5 times 10 to the 10 joule per cubic meter. And okay, quantum origin of this. So this idea goes far back to Zeldovich in 1967, and then was really popularized in a seminal work by Steven Weinberg in 1998. And this is known to be a big theoretical puzzle, which is also in the introduction like disturbing Captain America. So this theoretical puzzle, in very short, I don't want to spend too much time on it, but what is it? So in quantum field theory, you can either subtract all the background modes, but then you would not have a cosmological constant, or you can keep the cutoff of these modes, which is indicated momentum cutoff as kappa here, kappa 0. So then the energy density of a volume, energy density would be proportional to kappa to the 4th. And now you can compare. You can compare the quantum energy density with the cutoff to the energy density observed by the expansion of the universe, which is this y not here. And it depends on which cutoff you insert into this relation. You find that this thing is a very, very tiny number, 10 to the minus 120 or 10 to the minus 55, depending on which kappa you insert. And this generates a problem in the sense that if you want to interpret rho lambda in terms of rho q, this ratio should be 1. And there's another plot one can make. So you can plot this dimensionless ratio as a function of the cutoff or the mass of the cutoff. And typically you would expect 1. And now you can play and insert certain particles. So our mass is made of protons. And if you use protons, we are almost 50 orders of magnitude off. The top even more. And famously, if you insert the Planck mass, you're 120 orders of magnitude off. So this is the cosmological constant problem in a nutshell. And there has been a lot said and little understood by many at least. And so this theoretical puzzle is just a fact. Now, what is the idea of our paper is we would try to get some observational experimental input into this puzzle. And for this, we want to use the Casimir experiment to gain straight insight. So here again, the analogy of the construction side. So what we want to do, we want to change the quantum energy density by changing the Casimir energy density, which is supposed to be quantum, and then see whether rho lambda changes. Okay, that sounds pretty good. So let's think of small changes. Yeah, so rho lambda would then be different from rho lambda naught because you have changes introduced by this rho Casimir, and that's a parametrization. So you have the original cosmological constant energy density. We have a modification through the Casimir energy. This would then result in a net modified cosmological rho, which we call rho lambda without naught. And the parameter which is controlling this contribution, we call alpha. Yeah, so alpha is a free parameter of our working hypothesis. Thus, Casimir contribute to rho lambda. And so we can kind of go forward and see the relation between quantum and cosmological rhos, as was the idea. But wait, there's a little problem appearing, namely that the rho quantum in form of rho Casimir is in principle a local function. So it can vary where you look in your experiment, at which position, let's say. And since they are now connected to rho lambda in this equation, in the hypothesis, you cannot keep rho lambda as universal constant, just like we had it for rho lambda naught. So this does not work, and we need something which has as well lambda as a local variable, because rho lambda is constructed of lambda and g Newton. And so we need a framework which incorporates this possible position or scale dependence of lambda and g Newton. And well, there's a framework which is already developed. We don't have to invent anything new. And this is when you treat gravity as effective quantum field theory, you have similar effects, yeah? And this could be, okay, let's name some people here, Weinberg, Wetterich, Giddings, and many more are working on this field. And one crucial ingredient would be that the effective action in this approach has couplings which are not constant anymore. So let's indicate it by G is G of K, G Newton is depending on a certain scale, and this scale can depend in principle on your space-time coordinates, can be local. So we call this the variable couplings. And when you have this theory, this kind of theory, and there's a whole set of theories, it has two main consequences, which will be important for us. So one thing is that if you have this local properties, you get different Einstein field equations by just optimizing or varying the effective action. And the new contribution is read here, the delta T mu. Yeah. The other thing is that if you treat G and lambda as couplings of your effective field theory, and they vary, they are not independent. You change one and this changes the other. So they are connected in what is called the renormalization group flow. And here's just a famous picture from a certain approach to this. And the message is they are not independent. Okay, so let's look at the second thing. So the couplings are connected in something like an RG flow. And now in our setting, we are not interested in the high energy asymptotic region, but actually we are interested in the very infrared regime. And here we can just make an expansion of this scale dependence and parameterize this dependence. So we say in the infrared, K is now the scale. For small k is just G naught, so constant G Newton, plus a first contribution and a Taylor expansion in K squared. And the coefficient would be C1. The same is then true for lambda. And now we have these coefficients. And these coefficients have a different meaning for different people you're talking to. So if you talk to a theorist who works in this field, you would say, okay, I can go, I calculate my fundamental model, and I can predict you these coefficients. For phenomenologists, these coefficients would mean, okay, you assume these coefficients and you try to calculate observables for these coefficients. So that's our stake here. And the experimentalist ideally goes, okay, we have these observables, how can I measure or constrain them? So this is the connection between lambda and G. And since lambda and G are used to calculate the energy density rho lambda, we get this relation here. And now we see that rho lambda depends on the coefficients C1, C3, and also on K squared. And we didn't say what is K squared yet. We called it a scale which can be local. So let's now see how we can identify this scale. And for this, we just can compare. Yeah, we have now the expansion I just showed you through this possible connection, parameterized connection between lambda and G. And at the same time, we had the same expansion in our working hypothesis. We said rho lambda is actually rho lambda naught plus some modification through Casimir. And if both concepts are correct, then we can just subtract the two equations and resolve for K squared. And we then find that K squared actually has to be proportional to the Casimir energy density, as shown in this equation. So now we know K squared, and we can insert into the couplings back. And for example, for the gravitational coupling, we find something remarkable. We find that it's not just G naught, but it's actually G naught plus something with our parameters containing the Casimir, local Casimir energy density. And so here's where it comes from. It comes from K squared, of course. And so the message is G is not constant, but has this modification. So, okay, now we can go back to the modified Einstein equations. I show them again. And in this delta T menu, I will not show it, but it's just second derivatives of gravitational coupling and then divided out again by the gravitational coupling. So this modification of the Einstein field equations, which are actually necessary to maintain general covariance, does it affect Newton's law? To see this, we can elaborate a little bit. So let's use the trace tricks and just rewrite the same equations. They take this form, and here on the very right, you already see the second derivatives acting on 1 over G. So, and then we can insert stress energy for matter, which would be just this contribution at diagonal times the mass density, rho m, or mass energy density of the matter we are considering. In our case, it would be the plates. Yeah. Okay, to get to the Newton potential, we have to, or we can perform a weak field expansion. And in addition, since we have this delta T mu, assume a small or weak scale dependence. Yeah. So it's a double expansion, weak field and weak scale dependence. So here's the weak field expansion in the metric. You introduce potentials phi, psi, xi, and an expansion parameter, and the same for the scale dependence of the gravitational coupling. And then you go to just leading order in your equations and into lambda. But lambda actually is, for all practical purposes, very small. So now we look at the field equations and just the OO component, and we see that this is a typical Poisson equation of a gravitational problem where you have the mass density. But the new thing here on the very right is you have a modification due to non-constant g. That's what we call delta g. So here we have the derivatives of g. And we can solve these equations, of course, and here's the solution. It looks just the same as before, with a little modification that we have instead of rho m, now rho m plus a modification due to scale dependence, delta g, lambda squared. So, and this modification is then, of course, dependent on the local Casimir energy density. That's when we insert this here on the right-hand side. So let's go further. With this modification, one can go on and calculate the same modification for extended objects, and you have an extended modified Newton's law for extended massive objects, which is just written here. And formally, it looks just the same as we had the first formula we remembered from the beginning, but with a modification that rho m is replaced by rho m tilde. Same identification here. So let's summarize the scale-dependent framework. So we have two new features here. We have modified Einstein equations, and we have that the couplings are connected in the flow. And this results in the weak limit that the gravitational attraction between the plates changes. Yeah? So this is indicated by here that the Newton force F is not the same as the Newton force F tilde as soon as we have some non-vanishing vacuum energy density locally varying. And this means by measuring the Newton force, one can test the hypothesis we have been placing in the first place. So we can put bounds on the parameters of the hypothesis, which are alpha, C1, and C3, ideally. Yeah. So let's recapitulate what has happened. So we changed the vacuum quantum energy density by our working hypothesis that this contributes to rho lambda. But rho lambda is so small, it's not measurable in the Einstein equation. It would not make a difference, yeah? Measurable difference. But since this is a local quantity, we got help from this necessary scale-dependent approach. And from if you have this approach, it's natural to have a relation between lambda and g. So these are the parameters C1 and C3. And with this, you got modifications of g Newton, and this is measurable. So you got modifications from rho m to rho m tilde. And okay, now let's make a estimate, but let's make first propaganda for the planned CANX experiment. So this would be an experiment which would be actually hopefully able to measure such things, to measure, in addition to the Casimir force, also measure gravitational interaction. And I'm not an experimentalist, so I can show you the pictures. And okay. So now to the results of this, let's just make a preliminary toy estimate. So you can say that if an experiment doesn't measure modifications due to this rho tilde, then the rho tilde has to be, the modification has to be very small. So this means that these integrals have to fulfill certain ratio. And so what we need is basically a region where the derivative of G is not zero. And this is exactly the case if you think of a skin. Yeah? In the skin, the energy density would, for example, drop exponentially, and then the second derivative of G, and which depends on rho Casimir, is not zero. So you can say, okay, this correction introduced due to this exponential drop has to be much weaker than the actual gravitational interaction. So, and this would be just to get an idea, is this an important effect or not? And so you compare these things, and one finds that the contribution is actually tends to be very large, unless the prefactors, the parameters alpha and C1, are very small. So as indicated by this, very, very small. Yeah. Don't put too much weight on this number. It's a small number. Yeah. Okay. So now this is of course a remarkable result that this number is so small. So we have to be careful with the interpretation. So the first interpretation would of course be that our hypothesis is being tested. So alpha seems to be very, very small. So the connection between the rho Casimir and cosmological is strongly suppressed. It's also possible that lambda and G are not really related. That would have the same effect and would be represented through the constants C1 and C3. Another possibility is that the effective Einstein equations, which we have been using to derive this result, are not the right equations. So there might be additional fields in the Einstein equations. Some cancellations might happen, or new physics, let's say. And if this would occur, one would have to redo the calculation for this new physics model. So for all these interpretations, there's always possibilities. So let me mention something. For example, for the possibility B, there are sub-possibilities. So, for example, lambda is not a coupling but a field. G is not a coupling but a field. Then they will not be actually related, G and lambda. Or their renumeration group is not universal, so it doesn't make sense to apply this connection between lambda and G, and so on. So we got motivated by the cosmological constant problem. So let's turn to the first option. So let's turn to the option that alpha is very small. So what can we learn from this in context of the cosmological constant problem? So we have, again, the problem phrased as this ratio, and it arises in the essence from the ambition that one would like to express rho lambda in terms of rho q. And if this y would be 1, then the relation would be very easy and there would be no problem. Yeah? But y seems to be, or can be, actually a function of rho q. So, and in this relation and this problem, Casimir can contribute on both sides. Yeah. So up to now we have discussed how it can contribute to rho lambda, and that's our working hypothesis with the parameter alpha. But Casimir can also contribute to the quantum energy density with this cutoff, and the parameter for this contribution we call beta. So typically, if you talk to people, they either tell you, oh, beta is 1, and others tell you, no, beta is 0. So we don't know. So we also parameterize it and say, okay, there's a beta, finite beta. And now we can look with the measurement of alpha, it changes in the cosmological constant problem. So the derivative of y with respect to rho Casimir, and it's more evaluated at small Casimir energy densities. And what you find is a relation between y prime, beta, and y. So y naught is the cosmological constant problem here on the right, and alpha is actually measuring this. Yeah? If you measure alpha, you measure the other things. And that would be very interesting to have some experimental input into this connection. on both sides of the problem. The take-home message is the following. If rho c enters rho lambda, and the parameter for that is alpha, that's our hypothesis, and if scale dependence connects rho lambda g and lambda cosmological, the parameters for that are C1 and C3, then the corrections to the Newton potential tend to be big, not small, unless the product of these parameters, alpha C1 over C1 minus C3, is actually small. Because there's much more things we want to do and we're working on, actually. So we want to compare with quantum gravity benchmarks. For example, mentioning here asymptotic safety coupled to matter. So you have different benchmarks depending on the matter content, and then you have predictions of your of the parameters C1 and C3. We want to make more realistic simulation of a real Casimir experiment. Here, this plot is preliminary, but you would get something like an exclusion plot in the parameter space. And in this parameter space, you have the benchmark sitting of certain quantum gravity models. We also want to simulate not future only experiments, but also existing experiments. And we want to get more profound into the discussion and the implications for the cosmological constant problem. And much more. So thank you very much for your attention. Here are some references. And okay. That's all. So hope you enjoyed the video and